The Fundamentals of Physics, Part 1, the Basics. To learn any subject, we first need to learn the vocabulary associated with it. So, in today's lesson, I'm going to go through some common vocabulary, what it means, and how we're going to use it in the lessons to come. The first basic idea is the physical quantity. A physical quantity is something we can observe with our physical senses and quantify. For example, 3 dye, 1 cup of honey. I'm just going to use abbreviations, 25 seconds, and 10 degrees Celsius. These are all physical quantities. Now, what's in common between all of these? If you look carefully, each of these has a number, and each of these has a unit. And that's all it takes to be a physical quantity. Now, what isn't a physical quantity? Well, it's easy. Anything that can't be quantified, like love, wisdom, so abstract ideas. But also ambiguous terms. Like if I were to go to a grocery store and I ask the clerk, I want 7. And the clerk looks at me and is probably losing his patience at this point and is going to ask, what 7 what? So 7 is just a number. There's no unit. So we need a unit associated with it. So that isn't a physical quantity. In another instance, someone might ask me, how much time will it take? And I might just say minutes. And they'll say, okay, I understand that you're talking about minutes, but how many minutes? So in this case, I just have a unit, right? I just have a unit, but I have no number in front of it. So that's not a physical quantity either. Now notice, we use physical quantities in everyday life. And if we don't use them, things don't make sense. We didn't even know they were called physical quantities. So thanks, physics. Moving on, what really is physics? At least in a scholastic sense, we're usually solving problems. On a test, we're required to solve maybe 30 multiple choice problems. Solving these problems can be hard. And so I like to use modeling. Let's try to understand it with an example. Let's say your friend calls you over to play video games. She lives 6 kilometers away. How long does it take to reach your friend's house if you ride your bike at a speed of 10 kilometers per hour? Now, don't worry if you didn't catch that. I'm going to draw a diagram. That's the first step of modeling. So let's say this is your house and this is your friend's house. So let's go through the quantities. So the distance between your house and your friend's house is 10 kilometers. And you're traveling at a speed of, I got the quantities mixed up. So she's 6 kilometers away. And you're riding your bicycle at a speed of 10 kilometers per hour. And the question was, how long does it take for you to reach your friend? Now, the first idea I want you to notice is the point. We call it a point object. The house is a point. Both houses are points. You're a point. So we're not going to give quantity space, so as to speak. Even though technically they should have space, simplify everything with a point. If you're going to talk about an airplane, just make it a point and give it a label as P. So point objects. Draw a picture with point objects. And then next, what quantities do we know? So we know the distance, which is 6 kilometers, and we know your speed, which is 10 kilometers. Now at this point, there's a formula that's probably going off in your head. Speed is equal to distance over time. And if it didn't come into your head, don't worry, we'll talk about this formula. And we're really looking for what? How long does it take? So that would be time. So you want to solve for time here. So in case you're not good at math, I'll save you the trouble, but you want to understand this, okay? And then substitute the quantities. So you have 6 and you have 10. Now, a common mistake is not to put in the units, put in your units as well. So by the way, this is in kilometers per hour. Apologies. Kilometers per hour. And notice that these two cancel out. The hour goes to the top. So you have about 0.6 hours. That's the time it'll take for you to reach your friend's house. Now notice the simple steps, very simple steps. Read the question, draw a picture, make a list of what you know, get a formula, and finally substitute into the formula, cancel out things that you might not need, like the kilometer, and you have a final answer. And notice how the unit just naturally came in. You didn't need to ask yourself what the unit was. All right, so that's a simple example of how I like to use modeling. Always draw a picture. Maybe now you won't need it because it's a very simple problem, but as the problems get more involved and more difficult, having a picture is very helpful. Often in language, we have an issue where we overname things. Like we name the same thing in so many different ways, which really have the same meaning that one really questions, what's the point of it all? This problem is common in physics. Take length, for example. Length has about 50 units. Why does it need 50 units? Let me name a few. We have centimeter, yards, inches, light years, angstrom, furlong, nautical mile. It's just too much. And obviously scientists, they grew tired of this because now if they want to use data from different sources, they don't know what unit's going to be thrown at them. So scientists decided to standardize and create an international system of units. It's called the SI units. And they really consist of 7 units, but I'm only going to mention 3 of them. If you're curious, look them up. They're pretty cool. So these 3 quantities are time, mass, length, and the units associated with them, second for time. For mass, we have kilograms, and for length, yes, you guessed it, it's meters, not miles. The M stands for meters. All right? So these are important for our purposes because we're going to be using these units a lot, so get comfortable with them. In physics, we deal with very large or very small numbers, not only in physics, in everyday life almost. And it can be inconvenient to write these out every single time. So I'm going to shorten these numbers with a sweet rule, and we call this rule scientific notation. Let me give you an example. The Earth is about 4 billion years old. So let's try to write that out as a number. Okay, I think that's about 4 billion more or less. And, well, let's put a unit next to it. I'll put Y for years. The way I would shorten this using scientific notation is, the rule is, first write whatever you have as a number between 1 and 10. So, okay, 4.5. That's how, and the zeros you can just ignore, so 4.5. And then count out what you left. So multiplied by 10. How much did I leave out? 1, 2, okay, maybe I should make dots. 1, 2, 3, 4, 5, 6, 7, 8, 9. That becomes 10 to the power of 9 years. This is scientific notation. Instead of having to write all those zeros out, I can just write it out in this nice compact form. Let's take another example. The charge of an electron, it's a very small quantity. In fact, I'm not going to bother saying it. I'm just going to write it out, and yeah, you can just stare at how terrible it is. Okay, I'm done. I kind of regret now using this as an example. But let's understand this. How would I write this out in terms of scientific notation? First, just write the part that's not 0 as a number between 1 and 10. So that would be 1.6, right? And this is coulombs, by the way, not degrees Celsius, in case you were wondering. And let me not forget the negative sign. So there's a negative sign over here. I need to carry that over. Now, the decimal point part is a bit tricky, so I'm going to actually show you how to do this. Just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So it becomes 10 to the power. And since I moved the decimal point to make the number bigger, I have to pay up. It's kind of like having debt. So it's negative 19. It's how much you kind of owe. And coulombs, the unit. So this is how I use scientific notation. Sweet, right? Don't ever make me do that again. Is the world really what it seems? Now, we see things every single day and we say certain statements. Let me show you a quick example. So let's say you have a football player and the player kicks a ball, okay? And this ball is now headed towards the goalpost. So this is our ball and this is the goalpost, which is about, let's say 10 meters away. And the speed of the ball is 30 meters per second. All right. Now, is there anything wrong with what I just said? I mean, it seems pretty simple. Okay, the ball is moving at 30 meters per second and it's 10 meters away from a goalpost. How long will the ball take, let's say, to reach this goalpost? It seems pretty unproblematic, right? Seems pretty natural. Yeah, there's nothing wrong with the problem. But actually, when you scrutinize this, especially with the lens of physics, there are some issues because we're making a lot of assumptions which might not be very obvious to begin with. The first assumption we're making is that this 30 meters per second speed, right over here, is a speed relative to the ground. The second assumption we're making is 10 meters is not changing. This distance between that the ball has to go is going to remain 10 meters. In other words, this goalpost isn't really moving in time. It's just staying on the ground over there. So just to make these assumptions clear, because it might seem like I'm rambling at this point, the 30 meters per second speed is relative to the ground. So this is our first assumption. And the goalpost, I'll call it GP, is not moving with respect to the ground. So everything has to do with ground for some reason. Ground here has a special meaning. We actually call ground in this case the frame of reference for this problem. And that's kind of not very explicit. It's more implicit. So we're implicitly saying, okay, the ground is the frame of reference, everyone. But it was never really said in the problem. So a frame of reference is an important concept to think about. Our patch of ground is our frame of reference. That implies that we can draw a three-dimensional grid and associate a clock with that three-dimensional grid. So three-dimensional grids are like a bunch of cubes stacked up on each other. You can think of this repeating over and over and a bunch of these cubes all stacking up. All right, so that's a reference frame. And you might question, why even bother with a reference frame? I can solve any problem without one. Well, sometimes a lot of problems are simplified depending upon which perspective you look at the problem. For example, if you want to solve some physics problem on a train, maybe your reference frame should be one that's on the train. So your reference frame is actually moving along with the train. In other words, the reference frame is stationary with respect to the train, or the train is stationary with respect to the reference frame. And I know it might be confusing to think about, but having this idea of a reference frame early on when you study physics, and especially when you study Newton's laws of motion, simplify a lot of problems. And this picture of a reference frame might not be correct or accurate, but for our purposes, it's good enough. Thanks for watching. If you have any questions or comments, please leave them below. Until next time.